thanks everyone for being here. So today I want to talk about experimental design under interference. This is an audience where I probably don't need to motivate the importance of interference. One thing I do want to say, though, is if you sit in Silicon Valley, I think a lot of people in the kind of industry community there are kind of hadn't been worrying about interference that much for a while, and are now starting to worry about it a lot. The reason is essentially now, if you're something like an Amazon or an Airbnb or something like that of the world, you essentially are trying to run a small economy on a platform. And you also, when you run an experiment, your experiment might consist of nudging some people to behave differently. But the thing is, if you're running a small economy and one person starts acting differently, they're going to consume resources, they're going to kind of modify the incentive landscape for everyone else. So interference is everywhere, interference is ubiquitous. And kind of in many settings, this makes kind of experiments without considering interference just pretty meaningless. So just to kind of talk in the context of an example, and because I think this is a pretty easy example to follow, this is a model sort of motivated by ride-sharing. I think ride-sharing is nice because most of us have enough, at least a passing knowledge of ride-sharing, so I don't need to kind of explain what's going on there. Imagine that we have a platform that wants to get demand satisfied using freelance workers, and they do the following. There's a big pool of people who could potentially work with the platform. At the beginning of each day, the platform offers each of them a price PI. The workers see this price PI, based on PI, they could choose whether to kind of work with the platform per day or not. If they don't, they go away. If they do, they join the platform. Then once some workers join the platform, demand gets realized. And demand, if there's less demand than workers, then the demand gets allocated randomly to the available workers. If there's more demand, then some of the demand doesn't get served. And then we go on from there. And the question is, of course, from the platform's perspective, they might ask how should they choose PI to maximize revenue. If PI is too low, a lot of workers won't be active, so they'll lose demand. If PI is too high, then their margins grow. And so how would you want to run experiments for this? A first thing might be just like give different people different PIs and try to reason based on that. But this, of course, won't work because of interference. Exactly the reason I was talking about earlier, which is essentially, remember, we have a bunch of workers, we give different workers different payments, and then we randomly allocate some amount of demand to the workers who choose to become active. Now, if there's a group of workers who just choose to pay more, and let's say they like this, so by paying them more, they become more likely to become active, then now there are going to be more active workers, there's going to be more competition for the available demand, so then kind of the whole system gets less desirable for the people who didn't get paid more. So you need to control this interference. And people who work in this industry are well aware of this, so this is not news to them. And they're asking kind of what can they do to address this problem. And one idea that quickly comes up is, let's say if you're in the ride-sharing context, you might assume that two different drivers working in the same neighborhood would kind of cannibalize demand from one another. But if you have someone working in San Francisco and someone working in Seattle, probably their decisions have no effect on each other. So, easy fix to the problem. It's just run some policy in San Francisco, run another policy in San Diego, run a third policy in Seattle, see which one worked, and do inference based on that. And that does work. The problem is that you pay a huge cost in terms of statistical power. Let's say, for example, on a stylized model of ride-sharing, you were paying each driver $15 per completed ride. And then you were asking, maybe is this too low? Would the whole system run better if you started paying people $16? You could imagine paying everyone in San Francisco $15 and everyone in Seattle $16. But now let's imagine just when you run this experiment, it's rainy in San Francisco and sunny in Seattle. And the fact that it's rainy in San Francisco and sunny in Seattle has huge effects on demand and kind of the outside options of everyone participating in a marketplace. And this kind of completely changes the landscape of what you're observing. And these kind of weather patterns across cities dwarf the effect of your kind of small price changes. So the point is that you have to run this experiment for like many days until you get any power. So the question here is, given that we actually have some understanding of how this cannibalization is happening, it's essentially some people working more creates more competition for available demand, so that creates a disincentive to people who didn't get paid more. Can we use our understanding of how this interference comes about to correct that? So before talking about what I want to do briefly kind of mention what I think is kind of the prevalent approach in statistics to working with interference. Realizing, just thinking about this talk, I think like half the people I mentioned in this blurb right here, right, starting from like so-called Hutchison and Halloran, all of the classic difference in space. So really, if anyone here disagrees with what I'm saying, please come talk to me. So really, the prevalent approach to dealing with interference in this community is that if there's no interference, we have potential outcomes indexed by the treatment you receive. If there's interference, then we generalize potential outcomes and we create kind of potential outcomes, indexing also treatments received by others. And then you go from there, you have this notion of exposure mapping. And everything works well, and this lets you be kind of very agnostic about what interference looked like. It's just like, what matters to me is how these 5 people were treated, and then general potential outcomes, you can work from there. This approach essentially works if the exposure mapping is sparse, kind of the number of people who interfere with any other person is pretty small. But this doesn't really work in this problem, because in an economy context, like if there are 1 million drivers, I don't care which of the driver becomes active. I just care that some of the driver became active, any one of them, because they might take up demand I could have served otherwise. So with this approach, it seems essentially this approach pushes you to the randomize across cities world, but it doesn't let you gain more power about that. So what I'm going to do today is, maybe this is reflective of kind of, I sit down the hall from economists and maybe I hang out with economists too much. But I'm going to start modeling kind of behavior of drivers, and especially I'm going to assume that they're rational. They can kind of reason about what's going on in the system, and that what they care about is revenue. There are 2 things that matter in the model I wrote down, essentially how much you pay people, and then given that a person chooses to join the platform, what are their expected earnings? And I'm going to assume that workers don't actually care about these 2 numbers separately. They care about their product, which is revenue. It's a strong assumption, but empirical evidence seems to suggest that it's at least a reasonable model of worker-driver behavior in a ride-sharing context. And this creates a lot of structure, because it means that if there's any interference effects, this interference is modulated by total supply. I don't care about who chooses to be active or not. I only care about how many drivers choose to join the platform on any given day. So kind of starting from this assumption, and you can kind of like instantiate this with a slightly more concrete model. So what is going on here? Every day, I said the platform chooses payments PI offered to different drivers. Let's be a little more specific. Let's say the platform actually chooses a distribution pi, and then from pi for each worker draws a random payment PI that they're promised if they join the platform that day per unit of demand served. Then, given a choice of pi, then there's some large pool of candidate workers. Some fraction mu of them is going to actually choose to join the platform. What I'm going to assume is that the workers kind of know how to reason about this, and they know that if a fraction mu of workers becomes active, then the expected amount of demand they're going to get to serve is Q of mu. So they kind of know enough about the system that they know kind of, given the incentives chosen by the platform, this is what's going to happen afterwards. Then the point is that the expected revenue of each worker is PI, how much you pay them, times Q of mu of pi, that is how many units of demand they think they're going to get to serve, given that the platform chose pi, and this is going to make a fraction mu of workers to become active. Then they push this in some kind of choice function. Here I wrote kind of a logit model where they compare revenue to an outside option. The logit form here doesn't matter at all. It could be essentially anything smooth and differentiable. I just didn't want to write down regularity on the slide, so I wrote the logit. And then I'm going to assume the system is in equilibrium, meaning that kind of if each worker actually chooses to join the marketplace with probability, kind of depending on pi times q, then mu of pi matches the expectation of the activation probability evaluated at pi times q. Okay, the system's in equilibrium, and so remember the goal of the platform is to choose good choices pi, to choose how much to pay people. Essentially, then what they care about is revenue, so kind of pi leads to the kind of supply to be something mu, then given supply and demand, and T, they make some revenue, and they're going to go from there. But the hard part is kind of figuring out how different choices of payment map to different supply sizes. Okay. I mean, in a few slides, I'm going to go into details of like how exactly we're going to try to learn and find optimal payments. But before that, I want to just show a quick simulation study to kind of show evidence that it's kind of worth thinking about this, that if you're willing to go down this road, there are actually big power gains to be made. And so here's kind of the core idea of the method I'm going to talk about soon. We worry about interference, and our goal is to kind of choose optimal payments while accounting for interference. But in order to kind of learn about whether it be optimal to pay people a little more or a little less under interference, we need to start by measuring something. And an easy thing to measure is the following. Pick your target payment level P, and then instead of giving each worker a payment P, perturb everyone's payment with a small mean zero nudge. Give some people a payment Pi as P plus a small nudge epsilon or minus a small nudge epsilon. The point is that because you're not changing the average payment you're giving people, kind of under local linearity conditions, you're not going to change the expected supply side. So this doesn't trigger any interference behavior, and it lets you measure something. So here, what we're going to do is we're going to take these exogenous shocks to the payment. We're going to regress them against Zi, which denotes each worker's choice to become active or not. And when we run this regression, this essentially answers the question, if the whole system stays in equilibrium, if we kind of don't have any interference effects that kick in, how sensitive is the average worker to a small nudge in payments? This is kind of an interesting qualitative fact about the system. It's not of policy interest because it ignores cannibalization effects. So this delta doesn't correspond to kind of any decision variable that you need to take into account if you were wanting to reason about what would happen if you changed the prices for everyone. But it turns out that given our modeling assumptions, if you know delta, then it gets a long way to understanding policy relevant questions that will be relevant to kind of choosing an optimal P for everyone. Okay, I'm going to talk about how to get from this delta hat to a policy relevant thing in just a few slides. But first, a simulation. So here it's an experiment. We ran it over a kind of simulation. We ran it over 200 days. And the game is essentially each day the platform gets to choose a target payment level PI and then observe the reward. And they kind of, this is the kind of, you could call it the bandit setting, where you kind of learn on the fly. And you want to choose payments that give you good rewards along the sequence, but also let you learn the optimal payment eventually. And I want to emphasize that the way we simulate this, there are large demand fluctuations around days. You could think that sometimes it's sunny, sometimes it's rainy, and the market behaves completely differently when it's sunny or rainy. And two approaches we're going to compare here is something that's kind of an analog to experimenting across cities. Here we're going to say that kind of what happens every day is independent. So one way of learning is just like today I'm going to pay everyone $15, tomorrow I'm going to pay everyone $17, the day after I'm going to pay everyone $14. And you're going to try these different payments and you're going to try to learn from that. And you're going to try to converge. It's kind of a classical approach. And the second is the approach I'm going to get the details about soon, which is we estimate this marginal response function delta hat by kind of estimating the effect of exogenous payment perturbations on market participation. we're going to try to map from that to a gradient estimate of how does revenue change when you change payments, and then we're going to update the system by gradients. And on this slide, you see show results. So first on the right, you see a sample path from learning with our approach. So we start with a payment that's way off, like 30. We quickly converge to something near optimal around 17. And here, you see a comparison of the performance of global versus local experimentation along two measures. So on the y-axis, we're measuring kind of how good is the final payment you came up with. That is, if you kind of use the payment level you got in the last time period, how good is it? On the x-axis, you see how well you did in sample. And you see that kind of to the scale shown here, we get essentially 0 error relative to the global experimentation scheme. This is a striking difference. But then maybe it's not that striking, because for us the sample size is the number of people in the system, whereas for them the sample size is the number of days. And I'm going to show kind of formal results, and permitting that, or they're on the paper, that kind of show that in fact rates of convergence are completely different for these two approaches to experimentation. Okay, so how does this work? There are two main assumptions we're going to make. One is that days are different in a way that the platform can't observe, but workers can reason about. So here A might capture weather or something else. We're going to assume that conditional on A, everything concentrates in market size. And second, we're going to assume that we know something about how supply and demand match. That is that kind of given some amount of supply and some amount of demand, the number of matches actually formed, we can anticipate that, and it depends on the ratio of supply and demand. And given this, we're going to assume everything I assumed before except conditional on state A. I'm sorry, I'm going fast because I only have a couple minutes left. And in this situation, our main results are as follows. So first kind of two just reassuring results. Everything is, I said, kind of assumed equilibrium modeling. Fact number one is this model has a unique equilibrium. Fact number two is that as we kind of push the market size to be big, as we kind of increase the number of workers who could potentially join your platform, the system converges to a mean field limit, which is essentially the object I'm going to reason about now. Now something more interesting. Remember, the whole goal was to estimate these marginal response functions, which answer the question: if I give mean zero nudges to the, if I keep the whole system in equilibrium, but just random nudge up payments for one random person, how is that person going to respond? This is what we estimate using this kind of local perturbation experiment, and we can show that it converges to this thing under a model. Essentially, if you stare at this long enough, you could say that this is kind of a derivative of supply size relative to payments, but where you didn't take the derivative right. You only consider the part of the derivative factored in through payment changes, but not the part of the derivative that factored in through equilibrium effects, as you might expect. So really the key result is that this delta is a thing we could easily estimate using this local perturbation experiment. d mu dp is the overall derivative, that is, if we were to pay everyone more, how would supply size change? d mu dp is policy relevant but hard to estimate. Delta is not policy relevant but easy to estimate. The point is that under our model, we can write down a linear system that relates d mu dp and delta to each other. And there's a bunch of other stuff in this linear system too. Don't need to talk about it now. Essentially, the claim is that realistically, the person running the marketplace, all the other stuff in this linear system, they can get a handle on pretty easily. It just is a function of marketplace dynamics. The one aspect about the marketplace that kind of, it's not reasonable for the kind of platform designer to come an understanding of is what are the kind of outside options, the incentives, the preferences of people working the system. That is just somehow irreducibly mysterious. But the point is that delta captures everything you need to know about that. And so then if you have an estimate of delta, you have an estimate of d mu dp. From here, you can, if you have an estimate of how payments affect supply side, you can work up by calculus and affect how changing payments changes your revenue. And then what we're going to do, right, is every day start with a target payment, deploy that target payment plus or minus small perturbations, use these perturbations to estimate a marginal effect of changing payments. Then when you have that, use the model to map from this marginal effect estimate to kind of an actual policy relevant global effect estimate. Use that to get a gradient estimate of how revenue would change if you change payments. And then we're going to update this by, update the system by gradient descent. And the main formal result here, I'm going to have to refer to the paper if you're interested in details. We get a 1/t rate of convergence. So we get the good parametric rate. The noise comes from days being different. In contrast, there are lower bounds showing that the global experimentation scheme, the experiment that chooses different payments across different days, cannot get 1/t rates of convergence, even if you know that your revenue function is quadratic. The best they can do is 1/√t rates of convergence, so these are slow rates. So we get fast rates. The global experimentation alternative can get slow rates at best, so that kind of explains the big divergence in power in the simulations. I had more to say, but I don't have more time. So I'm just going to say thank you.
Time for 1 or 2 questions. Go for it.
I'm sure the economists who sit down the hall from you would disagree with me, but I find it hard to believe that the linearity truly holds in the perturbations, and I'm wondering, first of all, how you think about the plausibility of that, and second of all, if you could do some kind of sensitivity analysis that would have a single parameter for how far the equilibrium has shifted from where it was originally, and sort of get at it that way.
So, yeah, I mean, there are many things about this model that I think I don't believe in and no one believes in. We're trying to kind of write the first thing down. The linearity assumption, we were imagining we take the perturbation, nudge the perturbations to to make them very small.
Okay, so I was thinking then there's a trade-off between maintaining that assumption and power, and if you wanted to make the perturbation slightly larger, I wonder if there's a way to have a simple sensitivity analysis for the shift in.
So the way we did all asymptotics, and again, we sidestepped that issue. We kind of would do everything I said is true in the mean field limit, which is where there are a lot of people in your system. So then you can get away with infinitesimally small perturbations. But yes, doing a sharper version of this where you actually capture the second order effects would be very useful.
Yes.
I think another related thing that comes up is we kind of assumed a lot of rationality from the workers. It might be more plausible that people won't actually do this calculation, but they learn over time, and maybe there's some delay in that they don't immediately respond to payment changes, but it takes them some time to realize that, oh, now there's more competition, so I get to work less, and they respond to that. And would it be possible to kind of instantiate all of this, not in a setting where kind of hyper-rational workers, but ones who kind of learn from experience? That I would be very curious about figuring out how to do that, but we don't know.
Let's thank Stefan again, and we can continue this conversation.